Hi, this is Avi Pusula.
And Titus Sewell.
This is our formal lab report for Physics 273. So the objective of this lab was to create an experiment where we chose one variable that we can control in a collision and then vary that parameter and then explore how that affects the fraction of kinetic energy lost in the collisions.
Some key concepts to consider before diving into the lab are as follows. First, position graphs and velocity graphs and how they relate with each other, the conservation of energy, elastic versus inelastic collisions, and FMA, Newton's second law.
So the experimental design. So for our experiment, we decided to make a 2D collision in which we collided a ball against a wall at an angle. We kept all the variables relatively the same, and we only changed the initial velocity. And to accurately change the velocity, we used a ramp and increased or decreased its height in accordance to increase or decrease the ball's initial velocity.
After designing the experiment and considering the key concepts, we hypothesized that if a ball is going to collide against a wall at an angle with varying speeds, then the kinetic energy fraction will be consistent across all the trials regardless of its initial speed. We believe this is going to be true because though velocity is changing, the collision is going to be the same across all the trials, so the amount of energy conserved will be the same for each speed.
So to our data. So all the data that is highlighted in green is our initial velocities, and all the data that is highlighted in red are our final velocities. And we basically took all of those data points and wherever they were, and we calculated their average velocities for initial and final, and across all three trials.
Some additional diagrams to help with the collision are the system schema, which is the ball, which is what we're going to focus on. This is our system, and it's interacting with the earth and the wall. With the earth, there's gravity and contact, and with the wall, there's just contact through the collision. The energy pie charts. The ball starts with all kinetic energy right at the bottom of the ramp, and then right before the collision, after rolling for a bit, it has gained internal energy due to, friction. And then after the collision, more internal energy has been gained because of sound and friction, while kinetic energy has been lost and total energy has been lost due to the collision, and in the end, even more internal energy has been gained after kinetic energy has been lost.
So getting on to the calculations, since we were asked to find the kinetic energy fraction in the beginning of the experiment, we decided to go with the kinetic energy fraction equation. And then we derived an equation from that because we did not know the mass of the ball. So we basically got to a point where we could only use the velocity. So we basically derived it down to velocity initial squared minus velocity final squared divided by velocity initial squared. And using the data that we found before, we found that the kinetic fractions were 0.69 for trial 1, 0.64 for trial 2, and 0.69 for trial 3.
Some important trends in our data to notice. First, if we go back, we can see, here we are, that each graph has similar trends. It starts with some positive velocity that's higher, and then it goes down to a lower velocity after the collision. The next interesting thing is that the kinetic energy fraction for each collision is about the same, varying just by a little bit, and none of these are equal to 0.
These trends are important because they show that the following must be true. First, these collisions are all inelastic because the kinetic energy fractions for all three trials were greater than 0, which implies that the kinetic energy was lost over the course of the collision. Kinetic energy could be lost in a multitude of ways. First, there could be friction from the ball rolling on the ground. Kinetic energy could have been lost due to sound, due to the collision and the sound that it made during the collision, and a multitude of things. Second, the initial velocity of the ball has a very small and negligible effect on the kinetic energy fraction. This is important because it affirms our hypothesis that regardless of initial velocity, the kinetic energy fraction should remain relatively the same.